Okay, so last unit, global systems and energy. It's a short unit. There's nothing terribly taxing in it. Okay, so good news is if you continue to do what you've been doing, especially if you prepare like you did for your physics exam, this one is a real opportunity, okay, to keep that mark really high or make that mark a lot higher, okay, as the case may be, going into your final exam, right, which, by the way, is like 2 weeks after we come back. All right, so it'll come really quickly. All right. So what we're going over in the global systems and energy unit is basically some of the thermodynamic stuff we talked about in the last unit, but instead of in a mechanical way, this is more of a like biosphere wishy-washy way. Okay. Now, this unit in particular, we're looking at climate. Okay, this lesson, sorry, in particular, we're looking at climate. Okay, the components of climate, what is climate? Okay, all that kind of stuff. We're also gonna, most important thing, factors that affect climate. Okay, the effect of climate on plants, animals, and humans. Inputs and outputs in terms of energy. Okay, we talked about input energy, output energy in the last unit. Okay, and we're going to look at something called climatograms. Okay, which are an important tool in terms of climate analysis, climate comparison, and looking at factors that affect climate in different places. And we'll do an activity on that tomorrow. Okay. All right. What is climate? Without looking at the notes. Nice try, MJ. Okay, but you know when you ask that question of most people say the weather. Okay, the weather is what's going on right now. If I told you the climate of Okotoks was, that there'd be, a foot and a half of snow on the ground and, a wind blowing out of the west, well, that might be true. Okay, the wind blowing out of the west anyway. Okay, you'd probably say, no, that doesn't really accurately describe the climate of Okotoks because it's only like that part of the year, most of the year. Okay, you guys follow me there? Okay, but at the same time, if I describe to you, okay, the averages for Okotoks. So if I tell you the average temperature in Okotoks is about 6 degrees Celsius, okay, and I tell you that the winds are prevailingly out of the southwest, okay, and that we get 12 hours of sunlight and 12 hours of darkness, would you say that that accurately describes Okotoks either? I mean, it's the averages, but it doesn't really describe what goes on here. Climate is a bit more detailed. Okay, it's describing what you can expect in this area. Right? We should expect that things like light vary throughout the year. Right? I mean, right now we're approaching the shortest day of the year. Okay, where we're going to get like 5.5 hours of sunlight. Okay, and the correspondingly large amount of darkness. Okay, that always goes along with that. Okay, in the next few days here. Right? But in the summertime, we only get 5.5 hours of darkness on the longest day of the year, okay, which is also kind of nice. But it varies, and that has a big effect on things that go on here in terms of flowering plants and animals and stuff like that. When do they pollinate? When do they have their babies? It's an important, timing when you have your young is an important thing if you live outside, okay, because you don't want to have them right now. Right? Going into the coldest time of the year is not a good time, okay, to have little tiny baby, coyotes or foxes or ducks or whatever, okay, because they'll probably freeze to death. Right? That's why most of the young happen in the spring. Most of the mating goes on during the cold time, okay. But all of that stuff is related to our climate, and a lot of it's related to how much sunlight we get. Okay. Is wind an important factor? Does it affect things? Certainly it does, especially here, right? Because we got special winds. Okay, we get Chinooks, right? You say that word like in lots of other parts of the world, and they're like, "Was that like you speak an Eskimo?" Like, because it doesn't, right? It's a localized phenomena. You don't see Chinooks in a lot of parts of the world. Okay, but it's an important thing here because it greatly affects our climate. Okay, so those are the kind of things. The amount of rain that we get. Okay, is the amount of precipitation we get only rain, or do we count the snow too? We count the snow too, but here's the thing to remember. Snow, even though we can get large amounts of it sitting on the ground, doesn't have nearly as much water in it as a rainstorm. All right, all that snow we got last week, when that all melts, that might add up to maybe about 10 centimeters of rain. Now, granted, that's a lot, okay? But how much snow did we have? A lot, right? I mean, we all have snowbanks the sides of our driveway that are like shoulder high, okay? But there's a lot of air in snow, okay? It's frozen, right? So it's ice crystals and, like snowflakes, right? They're not, when they melt, do they leave a lot of moisture on you? Not as much as a raindrop, right? A raindrop has way more moisture in it, right? So things like that are important things to consider. It seems like we get a lot of precipitation in the winter, but the amount of water isn't nearly as much as we get in the summertime. Okay, we get way more water in the summer. All right, so all those kind of things are things to look at. So climate is the prevailing weather conditions at a location, not the weather today, not the weather tomorrow or last week. Prevailingly, this is what it is like. Okay, and this is an important thing because I almost always ask about this on tests. Okay, the major components of climate are the temperature. How hot or cold is it? Okay, the precipitation, the light patterns. You may want to just add in there light patterns. Okay, and wind. Okay, so those are the things that are usually described when we talk about climate. All right, now there's a big difference here. These are the components of climate. The rest of the lesson we're going to look at the factors that affect climate, and they are different. I don't want you to confuse the components of climate with the factors that affect the components. All right, things like our location affect the amount of light and our temperature and all of that. You guys follow me there? Okay, so factors and components are different things. Okay, now what do you see going on in this picture here? Okay, what kind of clouds are those? Cumulonimbus clouds, yeah, okay? When they start to get flat on the bottom and really tall and puffy on the top, or if they get flat on the top too, then it's really bad, okay? This is a cumulonimbus cloud. Cumulonimbus clouds are the ones that give us the thunderstorms that we get in the summertime. Now, it takes the interaction of a lot of these components in order to generate one of those. All right? What kind of days do we typically get thunderstorms on? Okay, it's got to be hot. What else? What's that? Generally not windy. Usually it's a little more calm because wind can disrupt their formation if it's too strong. Okay? How does it feel? Like it's hot, but it's also like humid. Yeah, it's really muggy on days when we get really good thunderstorms. Okay, those are days where it's really muggy. Okay, it has to be muggy because we got to have all that moisture. Okay, if we don't have moisture, you're not going to build one of these. Okay. Well, no, they can happen on a bright sunny day. I mean, as the day goes on, obviously it gets dimmer. But okay, we still want to have a fairly large input of energy. Okay, so we got to have sunshine. We got to have light. Because if they get flat on the top, means they're running into another, like almost like the jet stream, kind of that high. Okay, and that generally means that they're tall enough that hail will start to form. Okay, so what we got happening here, guys, is this. On a day where we're going to get a thunderstorm, we have a lot of heat, okay, and that heat is evaporating water. Okay, it's evaporating moisture from the land, okay, and that moisture is moving upwards. Okay, as it moves upwards, it cools, and what happens to water vapor as it cools? It turns into a liquid. Okay, it condenses, right? Now, that water condenses, it's heavy now, okay? It can't stay aloft, so it starts to fall. But as we build during the day, there's actually enough of an upflow of heavy, hot air that it can suspend these water droplets that are trying to fall. In fact, it can do more than suspend them. It can push them up. Okay? And that's why you see during the day the clouds getting taller and taller. Okay, as you see in this diagram here. So on the start of the day, you got these little tiny, cumulus clouds, late day cumulus clouds. Okay, but as it starts to develop, we start seeing, all right, there's a lot of heat here, and we're starting to see some heavier rain coming because more and more moisture is getting pushed higher and higher where it can condense. All right, when it starts to fall out, it's just getting to the point where, yes, there's hot air moving up, but there's so much condensed moisture above that it can't stay up anymore, and then it just pours out in buckets. Okay? If that continues and it actually prevents this heavy rain from happening, it pushes that stuff above, well above, the point in the atmosphere where the temperature is freezing. Okay? If you get a water droplet pushed high enough up into that cloud, what will happen to it? Yeah, it'll freeze, right? It'll turn into an ice pellet. Okay. Now here's the problem with that. Ice pellets hurt when they fall. Okay. But if they're small, it's just a nuisance. How do you get the big ones? Right. Okay. If you get a good enough cycling effect going on a hot, humid day and you build up a supercell thunderstorm, okay, you can get these water droplets cycling through this cloud a whole bunch of times, and each time they go a little bit higher and a little bit higher, okay? And if they get above the freezing point, they become an ice pellet. Then they start to fall, but they get pushed back up, and as they're moving back up, moisture condenses onto them because they're cold. That moves above freezing, that moisture that's condensed onto that ice pellet freezes onto the ice pellet. Now the ice pellet is bigger. Okay, goes through that cycle enough times, you start getting, the golf ball size hail. Okay, baseball size hail in extreme cases, softball size hail. Okay, largest one I've ever seen a picture of was the size of an ice cream pail. When melted, it contained over 3 liters of water. Okay, very extreme case, right? But obviously it can happen. Softball size hail is extraordinarily rare. Okay, picture a hailstone that big, right? And about, now it would be about 10 or 12 years ago in Wainwright, okay, they had softball size hail. Okay, it broke windows in houses, it destroyed roofs, and every car dealership in the town lost their entire inventory. Brand new cars and trucks written off. Okay? You ever seen what happens to a car when you throw don't try. Okay? When you throw a softball at it, okay? It leaves a big giant dent. Now imagine how fast something that's been falling from, a couple kilometers above you can be moving when it hits there. Okay? And if it's hard, it leaves a big dent. If it's soft, it splatters everywhere, but it can still leave dents and damage, crack windshields and things like that. Right? So huge amounts of damage caused by those kind. And then usually, if you're getting big hail, you're also going to get a what? You're going to get a tornado. Okay? And tornadoes form out of these because you have all this movement up of material, but no corresponding movement down. So you get a huge pressure differential. Okay, and that's when if you're watching the barometer, you can actually watch the barometer start to do this. Okay, and if it starts to drop, you're in trouble. Okay, when that barometric pressure drops quickly, okay, that means that there's got to be an equalization happen. All right, and the equalization comes in the form of a wind tunnel. Okay, that brings all that high pressure air from above down back to the low pressure area. Okay, and equalizes the pressure. Tornadoes equalize pressure very fast. Okay, so yeah, they're generally bad. All right, so those are the components of climate and how they can sometimes interact to produce localized weather phenomena. Okay, factors that affect climate. And I always ask a question about this on the unit exam, and I usually ask one on the final as well. Okay, that says, here's a city that you'd be familiar with, all right, or I'd show you a map of Canada and show you where it was. Okay, and I'd ask you, what factors would be most important for the climate of this area, and how would they affect its climate? All right, the one factor you can write for any place on Earth is latitude. Okay, latitude is the #1 factor affecting your climate. For this reason, it affects how much energy is received by that area. The further you are from the equator, the less intense the sun's radiation is. Okay, that's why if you go down to Mexico over Christmas, you're going to come back and look like a sun-bleached lizard. Okay, and the rest of us will all be like pasty white. All right, so when you go down to the equator, the reason you tan so much better down there is because the sun is directly overhead. Okay, and so its rays are very intense. Okay, they land on an area that's only this big here. So I'm just going to use a little tool here. All right, so the sunlight covers an area that's only that big, and actually I'd like that to be a little smaller. End up being a little bigger than I want it. All right, so that's the amount of area the sunlight covers there. Now, when it gets to here, oh shoot, I made it bigger. That didn't work. Okay, forget I did that. Go away. I don't want you anymore. Yeah. Okay. I'll do this the way I used to do it. Okay, so I'll draw this line here, okay, with the marker. So that's how much sunlight that is hitting that area. When I move that same length of line up here, okay, and tilt it, it's not quite as long, and it's even worse when I get up to here. Okay, it's not even close to as long, which means the same amount of sunlight's hitting, but it's hitting a bigger area. All right, which means it's less intense. All right. Okay, so right now, when the Earth is tilted away for us, when we're tilted away from the sun, okay, is that situation even worse? Yeah. Okay, that's why it gets cold here in the wintertime. All right, sure, we not only get less hours of sunlight, but the sunlight we receive is so diffuse that we don't really get a lot of heat out of it. Right? Whereas at the equator, okay, the tilt of the Earth doesn't really change very much. Okay, so if we're doing this, okay, so the Earth tilts kind of like that, right? When you're at the equator, does that really change very much how much sunlight comes in from overhead? No. That's why we got those special lines, right? The Tropic of Cancer and the Tropic of Capricorn. Those kind of mark the area where there's a significant effect, okay, season-wise, of the Earth's tilt. By the way, in case you didn't know, the Earth's tilt is what causes the seasons, okay? It's not because the Earth gets further away or closer to the sun. It does do that, but it has no effect on the seasons. All right. So we've got this kind of situation happening. So right now, if the sun is over here, okay, what season are we in? Winter. Okay. In the summertime, though, okay, we're tilted towards the sun, and of course that means that we stay in the sun a lot longer too, because the sun doesn't change. Okay, that's straight up and down. All right, so this is sunshine, and over here is darkness. So when we're spinning, okay, remember the Earth's axis of rotation is that way. When we spin, we stay in the sunshine longer during the summer. Okay, when we're tilted the other way, we spin, and we're over here in the darkness a lot more, which is why the days are shorter. Everyone follow me on that one? It has to do with the constellations that you are under. So when the Earth's tilt essentially makes some constellations visible or not visible, it's something like that. It has to do with those two constellations. So okay, so does that make sense? The effect of latitude. Okay, so the further away from the equator you get, okay, the colder it gets generally, because you get less intense sunshine. Okay, and that affects you no matter what city on Earth or what place on Earth you are in. Okay, if you are close to the equator, latitude means it's going to be warmer for you. If you're further away from the equator, latitude means generally it's going to be cooler for you. All right, questions there? Okay. The next one is altitude. Okay, altitude plays a big role in your temperature. Okay, in general, for every kilometer up you go, it gets about 6.5 degrees cooler for every 1,000 meters up. This is why the snow stays on the top of the mountains longer than it does down here. Right? It's colder up there. Why does it get colder the further up you get? Anyone ever climbed a mountain before? Why does it get harder near the top? There's less oxygen. The atmosphere is thinner. The higher up you go, the thinner the atmosphere gets, the less it's able to retain heat. Okay? And so it gets cooler and cooler. Not only that, but it gets obviously more and more difficult to replenish your oxygen debt. Okay? If you've ever seen like people climbing Everest, when they're getting near the top, they take like one step and they stop and they rest for like 25 seconds, and then they take another step and they rest. Okay? And these are people who could run back-to-back marathons at sea level. All right? So if you ever thought, oh, I could climb Everest, doesn't look so hard, think again. Okay? Not without significant training could you do that. Okay? And these are people, I mean, if you're wearing an oxygen tank, it's a little easier, but these are the people who do it the right way. Okay? Without oxygen. Okay? If you're climbing Everest without oxygen, you suffer miserably, okay, as you are climbing up the mountain. Okay, can you stay on top of Mount Everest once you get there? No. Okay. Once you get above a certain altitude on Earth, okay, and mountain climbers call it the death zone, okay, the reason is not because lots of people die there, but it's because if you stay there, you will. Okay, your body cannot maintain itself above a certain altitude. Okay, the pressure is too low. You cannot replenish your oxygen well enough, and okay, water begins to accumulate in your lungs and tissue. Okay, because you cannot properly move gases around. Okay, and in fact, at certain altitudes, you can get what's called the bends. Okay, you can get altitude sickness. Okay, and things like that. Nitrogen can start to bubble in your blood and give you really splitting headaches and stuff. Okay, it's generally very hard on your body to be in a very high altitude for a very long period of time. Okay, and you have to also be mindful of how quickly you descend. Okay, if you descend too quickly, that can have adverse effects on you as well. Yes, if you're a diver and you go from very deep water where there's an incredible amount of pressure and you come up too quickly, the same thing can happen. Okay, changes in pressure are bad for the human body. All right. Now, as you move up, like we said, it gets cooler. Okay, I took this picture. My dad and I were at Mount Robson. That's the mountain you can barely see there in the background. Okay, when we started, we were at an altitude of about 1,400 meters. Okay, and it was about 17 degrees. All right. The altitude we're at now, we're just above the tree line. Okay, we were at roughly about 2,600 meters. Okay, so it was a big climb. It was like warm, comfortable. As we went up, it got cooler and cooler to the point where it started to rain. Okay, but where we are right there, the rain had turned to snow. Right? Not because we were in a different place. It's simply because as we got higher and higher, it got colder and colder. Okay, and what was a kind of a driving rain became essentially a whiteout blizzard. And on the top of that mountain, okay, 2 people got blown off that day. Okay, we didn't climb up to the top because we're smarter than that. Okay, when there's a blizzard, you turn around or you die. Okay, when you're climbing, don't be stupid if you're a climber. Okay, getting to the top doesn't mean anything if you don't get back to the bottom alive, because you generally get back to the bottom one way or the other. But okay, so yeah, okay, so you can see here the effect, right? Like here in this picture, like where we are, it's kind of rainy, but up here it's clearly snowing. Okay, the higher up you go, the colder it's going to get by about 6.5 degrees. Okay, so something to be mindful of. That's why a place like Calgary or Okotoks is generally cooler than a place that has the same latitude, okay, but lower altitude. Okay. What's that? Yeah, Vancouver also has some other factors in that it's close to the ocean, and the ocean is a big effect on temperature, which is one of the next ones we'll talk about. But yeah, I mean, if you were to look at, let's say, Calgary versus, let's say maybe, Regina or something like that, similar latitude, but Regina's a little lower. Okay, makes a big difference. Okay, and in fact, you can even see it in town here. Sometimes when you come up to the school, we're at one of the highest points here. We're at about 1,100 meters. Okay, it's sometimes colder here at the school than it is down in the river valley. Okay, and that's only a difference of what, maybe 100 meters. Okay, but you can tell differences sometimes. All right. Distribution of land and sea. Distribution of land and sea is huge. Okay, because in very few places in the world does the ocean actually freeze. All right, yes, sure, at the North and South Pole, there's the ice pack in the ocean. The top of the ocean at least freezes. Okay, but most places, it doesn't. All right, the temperature in the air may be well below freezing, but the ocean doesn't freeze. Why not? Well, to some extent, there's salt in it, but it doesn't freeze because it doesn't get below zero. Okay, you got to consider, guys. Every ocean on Earth is essentially connected to all the others. Okay, are some parts of that ocean very, very warm? Yeah. Okay, and water has a very good ability to hold on to heat. All right, and so it can regulate the temperature of the air surrounding it, which is why a place like Vancouver, okay, and Victoria are typically a lot warmer than most Canadian cities. Vancouver and Victoria are about the same latitude, close to Calgary. It's significantly colder here because we're not anywhere near the ocean. The ocean can regulate the temperature of the air. All right, so even though a cold air mass may move on down there, the ocean, because of the second law of thermodynamics, heats the air. The ocean doesn't get that cold, right? It stays above zero. And so heat starts to come from the ocean to the air, warming up the air, and the air stays above freezing. Okay, or at least it doesn't get like to be minus 20. All right, you guys follow me there? All right, so being near the ocean has a huge effect on temperature because of the ocean's ability to retain and transfer heat energy. Right? Right. So inland, though, where we don't have that, okay, our temperature can fluctuate wildly, right? Because we don't have a stabilizing influence, okay, like Victoria does. All right. Now, you think of another city that's near the ocean, go out to the East Coast, okay? Does it get wickedly cold on the East Coast? It does, okay? Different type of ocean, though, okay? Here on the West Coast, you've got, okay, ocean currents that are coming from more equatorial areas. Okay, they're coming either straight east-west, or they're coming from the south and kind of coming up this way, bringing warmer water. All right. Whereas over here, okay, in Newfoundland and Labrador, where are the ocean currents coming from? Yeah, they're coming out of the Arctic Circle, out of the Arctic Ocean. Well, that's not going to be as warm a water as this stuff, is it? Okay, well, that's going to bring in colder air masses, things like that, and so you do get cooler temperatures here, and you do get the ocean freezing, okay, from time to time over there because of where the water's coming from. Okay, if it's coming from more tropical areas, you get warmer weather. It's coming from northerly areas, more northerly weather. So the East Coast and the West Coast, even though they're both close to the ocean, are affected by it differently because of where that ocean water comes from. Okay, the other ones that you may have heard of. Okay, El Nino and La Nina. How many people have heard of those before? Okay, if we get a really unseasonably warm winter, people are like, oh yeah, it must be an El Nino year. Okay, if we get a really wickedly cold one, then it's a La Nina year. Okay, these are the result of an ocean current that actually happens down in South America, off the coast of Chile. Okay, there's this huge upwelling of warm water that happens down there in the Pacific, and it can alter the temperature of the ocean by a couple of degrees. Okay, now, that may not seem like very much, like 2 degrees. You wouldn't even notice that, right? Except when you consider the volume of water involved, is that a lot of energy? Yeah, it's an ungodly amount of energy. And that, even that small change of a couple of degrees, can make it unseasonably warm here for an entire winter. Right? Those are the years where we don't have any snow at Christmas, okay, things like that. Right? Whereas, okay, in a La Nina year, that's where your Halloween costume has to be designed over a parka, okay, because winter starts in September, okay, and lasts until June, right? Okay, those two make sense? Okay. Distribution of mountain barriers. Okay, mountain barriers have huge effects on climate because of the effect they have on moisture and the winds that they can cause. So for us, this is one of the biggest factors that affects our climate. We are very close to the Rockies here, okay, and we are in what's called their rain shadow. Now, the rain shadow of the Rockies isn't too bad, okay? There are bigger rain shadows in the world than this one, okay? But it's noticeable. So, warm, moist air comes off the Pacific Ocean and hits the mountains. As it hits the mountains, it gets forced upwards, okay? So it's going this way, up and over the mountains. As it goes up, it cools, and the moisture condenses, and it falls on what's called the leeward side of the mountains, okay? Sorry, I said that wrong. This is the windward side. Sorry. Okay, and this is the leeward side. Okay, on the windward side, the wind is coming in. Boom, it hits the mountains here, and all the rain falls. Okay, all the moisture falls out of the air on this side, and the air that's coming is getting cooler because it's getting forced up and over the mountains. Once it gets up and over, it's now cool and dry. Okay? As it comes down off of the mountains, it picks up energy. Okay? Because gravity's pulling it. Okay? It starts picking up energy. It's encountering and interacting with the ground, with the mountains, with the surface of the earth. Okay? And as it does that, it warms up. Okay? It warms up, but it stays dry. What do we call a warm, dry wind that comes off the mountains? This is how a Chinook is born. Okay, now there's other factors, pressure and things like that, but that's generally how it works. Okay, the effect of a Chinook, however, in addition to the desirable effect, it gets a little warmer, okay, is that it dries out this area. That's why you see prairies or desert on the leeward side of a mountain, but you see temperate rainforest, okay, or in some cases even tropical rainforest on the windward side. Because on one side of the mountains, all the moisture drops. On the other side of the mountains, it gets sucked away by the dry air that's coming off. Okay, one of the other places you can see this is in Asia, on one side of the Himalayas versus the other. Okay, the Gobi Desert is the rain shadow of the Himalayas. Okay, it is a cold, dry desert. Okay, if you look at Hawaii, look at many of the Hawaiian islands. Okay, on one side of the island, it's usually dry, and on the other side of the island is a jungle. Okay, almost every Hawaiian island is like that because the wind comes in on one side, gets pushed up over the volcano, all the moisture falls out on that side, and it's dry on the other. Okay, if you've ever been to Hawaii, look for it. Okay, every island is like that. Okay, there's a dry side and a jungle side. Yep. Okay, so this is a big deal. This one is probably, other than latitude, the biggest one for us. Okay, the mountains are probably the biggest factor affecting our climate. Okay, patterns of prevailing winds. Do we have prevailing winds here? Prevailingly they come from? Okay, yeah, from the which direction? Southwest, west, yeah, somewhere in there. Okay, typically that's where it comes from. If the wind's coming from a different direction, do we know there's a change coming? Yeah. Every time the wind blows out of the northeast, the weather gets sucky. Yeah. Okay, doesn't matter whether it's winter or summer. Okay, the weather gets worse every time the wind comes out of the northeast. Nothing good weather-wise ever comes from that direction. Because what's it bringing? Cold air. Okay, it doesn't necessarily mean it's bringing moisture. There isn't a lot of moisture up in the northeast from here. Okay, but it's bringing cold air. If we have a moist air mass sitting over top of us and a cold air mass moves in, it'll cause a rainstorm to happen. Okay, because it'll start to condense that moisture. Okay, and when two big air masses that are very different interact, that's typically when you get very unsettled weather. And we just happen to be in one of those areas where they tend to channel. All right, there's another area in the central United States where that also tends to happen. What do we call this area? That's Tornado Alley. Okay, well, guess what? Tornado Alley doesn't just down here, okay? We get one too. The mountains cause this effect here, and we get kind of I mean, where's the worst place to be if you're on Highway 2 when the storm comes? Like right around Olds, right? Okay, that's like the worst place. That's where it just seems to all gather and meet, and then it channels right down Highway 2. Okay, all the weather always seems to channel right down Highway 2. Highway 2 is built right in the chute, okay, of this bad weather. All right, and so that's why it always gets so nasty, right? Okay, it's built right through here, right? This essentially runs Edmonton to Calgary right there. Okay, right in between, and that's why it always gets so bad. Okay, so to areas of high and low pressure. There are some areas that are typically high pressure and some areas that are typically low pressure. All right, and if you ever see a weather map, kind of like this one here, okay, you'll almost always see right in here is low and right in here is high. For some reason, they just seem to always collect in those areas. In fact, lots of meteorologists call this area here the mother low because she gives birth to little low pressure areas that kind of tend to fly off, okay, and come down the chute here, okay. And then there's this. Meteorologists often call that the Siberian high because it's usually high pressure there, okay. If in the wintertime we're in a high pressure area, what kind of weather do we get? Anybody know? If we got a high pressure area sitting on top of us, what's the weather like in the winter? Yep. It's clear and dry and miserably cold. Okay? That's one of those days where you look out the window and it's like, oh, it's a sunny day outside and it's minus 40. Okay, right? That's what you get when you got a high pressure area sitting on you in the wintertime. All right, because all the heat just bleeds away. It can get right out. There's no clouds to hold it in or anything like that, and it gets really, really miserably cold. All right, in the summertime, high pressure area usually means the opposite, because then the sun can beat down on you, okay, for 16 or 17 hours a day. All right, so it's quite a bit different. All right, now again, we were talking about how the location of this high pressure area and this low pressure area can cause climate interactions. If you live here in like Prince George or someplace like that, okay, it's often very rainy because low pressure typically means rain. High pressure typically means clear. All right, but if you live in this area, that means weather can rapidly change. Right? We have the expression weather in Alberta. Don't like it? Wait 5 minutes. Okay, well, the reason being, we're at the whim of these two steady areas. Okay, something comes off of that low area, it comes in this way, okay, off the high, and they're always interacting right down the middle of the province, okay, giving us those rapid weather changes. All right, the thing we're going to be working on tomorrow, climatograms. Okay, climatograms are graphs that essentially show some of the components of climate. Okay, the most important ones anyway. Okay, don't pack up yet, guys. You got a few things here you're going to probably want to write down about these. Okay, on a climatogram, okay, you've got precipitation on one side and you've got temperature on the other. So this graph actually has two y-axes, but it's not a line graph. These are bar graphs. Well, it's actually a line graph as well. Okay, so typically what you see here is the bar graph is measuring precipitation. Right, so the bar graphs for precipitation. Okay, so this is precip. Okay, the line is temperature. All right, so on a climatogram, you draw a line graph for temperature, you draw a bar graph for precipitation, and you typically show the patterns. Now, this is useful because when at a glance, you can tell, okay, where someplace is without even having to look at the name on the top. Okay, look at this temperature line. It's flat. What does that mean is this area does not have? Yeah, it's near the equator and it's not, there's no seasons, right? There's certainly not a winter summer, okay? It's like 25 degrees, 26 degrees the whole year, right? Its temperature doesn't fluctuate. As soon as you get a bell curve like this, you're moving away from the equator because now you've got a definite summer and a definite winter. Okay? This bell curve moves. The further away from the equator you get, the bell curve drops. Okay? So you're looking here, this is Anchorage, Alaska. Okay? Look at where the bell curve is. Now Anchorage is actually temperate when you consider that it's closer to like the ocean. Okay? But you know, in the wintertime we're looking at minus 10, okay, as an average daily high. Okay, you know, if you were to do this for like someplace in Nunavut, that bell curve would drop even more. Okay, cool. They get some lake effect weather, certainly. Okay, you know, the St. Lawrence and everything like that. Yeah. Okay, the Great Lakes are a good enough sized body of water that they can affect weather. If you live in like Buffalo, then you get the lake effect snow, right? You've seen like stuff on the news where Buffalo is digging out from under 6 feet of snow, and that didn't happen over like 4 days. When they get lake effect snow, it happens overnight. Okay, they'll get several feet of snow in hours. Okay, when they get lake effect snow. Yes, that's what we're going to do tomorrow. Okay, so what we're going to be doing with the climatograms, guys, is this. Okay, we're going to be looking at we're going to make climatograms for a bunch of Canadian cities. And then we want to look at them and go, okay, well, these Canadian cities have these similarities, these ones have these similarities, and then compare them on a map. And what you'll find is the ones that have similar shaped climatograms are located in similar places. All right, because the factors that affect their climate are the same. All right, so you're looking at, you know, let's say, you know, Edmonton, Calgary, you know, Lethbridge, they're going to have obviously very similar climatograms because they're all kind of in the rain shadow of the Rockies. Okay, they're affected by the same things. Okay, if you look at even probably like Saskatoon, Regina, Moose Jaw, they'll even have similarities to those. Okay, it'd be like a prairie climate kind of an idea. Okay, you'd have a central Canadian climate looking thing if you're looking at Montreal, Toronto, Ottawa, okay, places like that. They'd have very similar shapes. The Maritimes would all have similar shapes, things like that. Okay, so that's what we're going to be looking at. Drawing some climatograms tomorrow, and then looking at why are these cities the same? Do they have factors that affect them that are similar? Okay, so it'll be kind of an exercise to just work with that stuff tomorrow. Okay, questions there? All right. Okay, just quickly answer those questions there, guys. Those questions for review.